This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us today for another Satellite Book Club. This is part of the seminar series, session number 28. We're pleased to be joined today by Karen Eagle, who is the meteorologist in charge at the Denver Longmont Center Weather Service Unit and is currently on assignment to Central Region Headquarters. I'll be facilitating today. The title of Karen's talk is Detecting Turbulence via GOES Low-Level Water Vapor Band. Just a few announcements before we get started today. First, you just heard the announcement that this session is being recorded, so if you have a colleague that is on shift right now or unable to join us, they can find this recording on the VLab in the next couple days. There'll also be some time for question and answer after the presentation. Please use the chat feature and just type your question in as it comes to your head, and we'll address it during the Q&A session. As a reminder, we're always looking for future presenters, so if you have a potential application that's relevant to our field offices, we're looking for science officers, forecasters, even some researchers. If you have an application, please feel free to get in touch with us. And if you're looking for training, there's training materials that are available. Brian Mata can help you. He's got a great team of our affiliates at the universities that create training materials and can help you locate the materials that you need. I'd just like to thank the Tower S team, the Office of the Chief Learning Officer, GOES-R, and JPSS. And before we get started with Karen's presentation, I'd just like to give a time for a brief introduction from Kashad Bowman, who is our new coordinator for the Satellite Book Club seminar series. Kashad, welcome.
Hello, everyone. Yes, my name's Kashad Bowman, and I'm a new member of the Tower S team. And I just wanted to say, give a quick thanks to Jordan Girth and Ms. Karen Eagle for allowing me a chance to introduce myself today. But we at the Tower S team are very appreciative of your feedback and input. So if you have any questions or concerns, please direct them to myself. Thank you.
Thank you so much. And Kashad, my understanding is you just graduated. Where'd you graduate from?
Oh, yes, I went to Mississippi State. I graduated in December of 2019.
Okay, wonderful. Well, we're glad you have us we're glad that you are with us. And thanks again for your help today and in future Satellite Book Club seminar series.
Thank you so much, Jordan.
All right, without further ado, I'd like to introduce Karen Eagle, who's an expert in aviation forecasting. She spent the majority of her career as an aviation meteorologist at the Aviation Weather Center in Kansas City. In 2019, she transitioned into management, became the meteorologist in charge of the CWSU at Denver Longmont. Most recently, she is on assignment with the Office of Human Capital Services, Performance Culture and Learning Branch, working on marketing, branding, and communications for the new NRAP, which I think is coming out soon. So many of you probably know, but similar to the AWC, the CWSU focuses on en route traffic and will issue center weather advisories for aviation hazards such as icing, turbulence, and convection. Along with en route traffic hazards, forecasters at the CWSU focus on several underlying facilities. In the case of Denver Longmont, that's the Denver International Airport and the ski country in western Colorado, which I think more specifically is the Eagle, Aspen, and Rifle airports during the winter months. So Karen, really looking forward to your presentation. Thanks for being here and welcome to the Satellite Book Club.
Thank you so much. I'm so happy to be here. It's exciting to be able to talk about turbulence and aviation weather in general. This is really exciting. I'm thankful that I was invited to come and do this. So let's get started. And appreciate the extensive intro. That was pretty nice. So let me make sure I'm doing it. See, I already messed up. Okay, so I wanted to kind of go over a little bit of what the AWC does, since I spent the majority of my time there, and that is where this case actually started from, or when I was actually working there. So this is the area of responsibility for AWC, and as you can see, it's quite large. The AWC actually has 8 forecast desks, and they have 2 different branches, an domestic operations branch and an international operations branch. In the domestic branch, the 5 desks are going to be for basically over the domestic and the waters there, basically over the United States and the waters adjacent to the United States. And so the 3 desks, they actually are element based. They forecast for turbulence, icing, low ceilings, and visibility. And again, that is for the entire United States. There are 2 convective desks as well, and those 2 desks, one actually is only seasonal and runs from October through March, and then that's the TCF desk, which is the Traffic Flow Management Convective Forecast. And what that really is a unique desk in the sense that the forecaster there actually hosts every 2 hours hosts a chat with other meteorologists across the country to decide on convection where it's going to be. And what the FAA does is actually use that to their advantage and their planning purposes in the morning and throughout the day to help them decide the traffic routes across the country. And then the other desk, the other convective desk, is the convective SIGMET desk, and that is actually issued every hour, product every hour. And the SIGMET is actually a warning, and that's a warning for convection. Then there's also the international branch, and there's 3 desks for that branch. 2 are for the global graphics, and that is each forecaster is taking half of the globe, and they're forecasting for convection and turbulence and other things like jet streams and things of that nature. And then also the other desk is the tropical desk, and you can actually see on this photo here what the tropical area of responsibility is, which is here in between the Alaska and Hawaii airspace, and then out over the eastern part there of east of the country. And you can see how it's pretty large, and they take care of icing and turbulence as well, but mainly in the form of SIGMET, so for warnings for traffic that's moving across the oceans area. So this case was really exciting for me. This was in the summer. It actually happened on July 8th of 2017. And typically in the summer, we just don't see a lot of turbulence. And so I actually was on the day shift this day and was putting my forecast together. And I typically do my forecast by pattern recognition versus looking at model data for turbulence. And so I started out by looking at this as an upper level map of 200 millibars. And just by looking at this, you can see here over the western part of the country, we do have a high pressure system with very light winds. And then we also have a trough over the northeastern part of the country from the Great Lakes up to the northeastern, basically up to Maine. And with that, that's pretty light. Didn't see a lot of turbulence with it and no shear really. And so I ended up issuing no air meds. And an air med is basically an aviation advisory for air traffic. And so that was the forecast was due at 15Z, excuse me. And so I did not have any turbulence issued for that package. Well, later in the day, actually, sorry, excuse me, I got a tickle in my throat. Also wanted to kind of go over this too. So this was the surface pattern. You can see here there was a front that was down through Montana into central Nebraska, and then all the way, and then, well, actually broke over Kansas and then through northern Arkansas all the way up to New England. And again, not something that I would really focus on in terms of turbulence, especially during the summer. So did not, like I said, I did not issue any advisories or any air mets for that day. Then through the morning period, I actually did start to get some pilot reports. And what a pilot report is when the pilots actually are flying through any type of problem, and it could be icing, convection, turbulence of any kind, they actually will send that information to us to let us know what they are running into. And in this case, they were running into turbulence, which for me at that day in the summer was pretty shocking. And so what I ended up doing is I ended up bringing up this model, and this is the NAM model. And what you can see here over Texas, and I did overlay the pilot reports here, is you can see that we started to get several pilot reports through northern Texas into parts of western Oklahoma and even all the way up into southeastern Kansas. But overall, the model, which is this green here, did not really show a lot in the way of turbulence. So I was really confused as to what was going on and what they were running into. And at the time of this case, what was unique about it was we had actually just had, a few months before, we just started using GO 16. And so I wanted to be able to see what, to see what we were actually looking at. But I also wanted to further investigate. So what I ended up doing was look at this model, notice that I didn't see a whole lot. And then I went and started noticing, what levels these pilot reports were on. So you can see here, this is 31,000 feet, this is 33,000 feet, 35,000 feet. And then I went to our sounding, and this sounding is one of the things that we use to kind of get an idea of where turbulence is up in the atmosphere. And these were falling right here in between the 300 millibar and 200 millibar airspace. And mainly what was going on was there had to have been some wave action that was bouncing between these two stable layers. But I wasn't able to see that. So if you're not familiar with the national centers have two computer systems. One is NRAP, which is where all of the forecasting is done and the products are issued on that. But we also had AWIPS. And so AWIPS, for me anyways, was something that I used for also model data, but satellite data as well. And so satellite in general, once we got GOES 16, was very useful for us. So that is actually what I turned to see what I could not see on NRAP. And so Lee, if you want to show the satellite, we'll go to that. So this is the satellite from that day, and we started the loop at about 12Z, and you can see here that can't really see a lot, mainly through here. There are some clouds and there's some dying off convection through the parts of Oklahoma and Texas and even into western Kansas, but overall not really a whole lot in the way of what I would consider an area where I would get turbulence, especially here in northern Texas and in western Oklahoma. There was really no clouds of any type. So that was peculiar because I wasn't able to see anything. You can also pick out some features here, which actually I'll show in the water vapor. But again, here, this is the IR. Again, you can't see a whole lot, especially as this old system that's dropping into parts of Colorado, I'm sorry, not in Colorado, parts of Oklahoma into western Arkansas. Other things to point out, we do have, actually go ahead and go to the IR, I'm sorry, the water vapor, we'll go to that. Okay, this is perfect. So what you can see here is there is actually a little feature here, and I'm looking at the top left one here. There actually is a little feature that's starting to drop down. Yeah, thank you for zooming in on that. That's starting to drop down from Nebraska into parts of Oklahoma and Texas. And that's not something that we could actually see on satellite. You can actually, for comparison's sake, you can see that in western parts of the IR, in western Kansas, you cannot see really what's going on there. So this was really intriguing to me, and I remember this day very distinctly because I was super excited for the first time I was able to actually see turbulence on satellite. And so the setup for this was actually, these are some dying thunderstorms that were occurring over the night with an MCS, or a Meso-Scale Convective System. And what it ended up doing was it actually created an MCV, which is a Meso-Scale Vortex. And that was actually where we were starting to get some turbulence. And can you zoom in just a little bit more there in western Texas? I'm sorry, western Kansas and Texas area. Yeah, so go back a couple of frames. I'm gonna actually have you stop it. We can show, keep going through. We'll show you where the waves started to occur. Okay, stop it there. So right here is kind of where we started to see, this is the feature right here in southwestern Kansas, and you can see there's this little feature that's starting to drop down into Oklahoma, Texas. And you can move forward just a few more. We actually can see the waves that are starting to develop and cause problems. So there's the waves that are starting to develop there. And you can see that there in western Oklahoma and southwest Kansas. And then now, of course, really you can start seeing those two waves There's a couple of waves there in Oklahoma and not really into Texas just yet. Also, there's a lot of things going on here. There's also another dying MCS that's moving through eastern Oklahoma. I keep calling it Colorado. Eastern Oklahoma, and then you also have some leftover cloud debris that's through Kansas into parts of southwestern Missouri. So all of that added up to this area of turbulence. But the main focus for this day was this area here in western parts of western Oklahoma and southwest Kansas. And so once I noticed that, and also with the pilot reports that I was getting, I decided that it was time to issue an amendment. So I did actually send out an amendment that day for, let me share my screen, for a couple hours just to make sure that the pilots that were actually traveling through there were able to know that there was something that they needed to avoid. And again, I did use this is the SKU-T, and I did use this to show the area or show the heights where this turbulence was occurring. And you can see here on this SKU-T from 200 to 300 millibar, you have a very slight area that's going to be where you're going to have some stability, and the waves are going to be bouncing between those two stability layers. And so then I also want to just quickly go through kind of some of the other model data, excuse me, that they use at the Aviation Weather Center. There we go. So this is the LROD index, and this is a busy slide, so I'm not going to go through all this. But this is one of the main things that we used to use, or they use at the AWC in terms of LROD, and actually the CWSUs can use this too because it is online. Which is very handy, and it just shows areas of shear. So what I would normally do is I would actually go up to, and I'll show you again, I'll go back to this slide where I would actually go through and look to see the pattern. In this case, a high pressure over the west and a trough over the northeast, and see where there were any types of turbulence or shear. And if I would see an area that I would consider that would have a lot of shear, I would then go back to use this model, which is a part of the LROD suite, and which is this. And then also we use the Richardson number, which you all know has to do with shear instability. So anything less than 0.25 could usually determine that there's going to be some type of shear in the area and that you'd want to probably issue an AirMet. So it was very interesting that day with being able to use satellite. We hadn't had a satellite go 16 for very long. And I just remember being able to see turbulence for the first time, and it was really exciting. So I'm thankful that I was able to give this presentation today, because one of the things that I want forecasters to realize is that, especially with the national centers, is that you can use AWIPS for forecasting and then noticing different types of waves in the water vapor. For me in particular, I preferred the lowest wavelength, which I think was channel 10. And so I enjoyed using that, especially for any type of wave activity, and mountain waves as well is very handy. So that is all I have for a presentation. It's quite short, but again, I do thank everybody for coming, and I hope I was able to enlighten you a little bit on turbulence forecasting.
All right, thank you so much, Karen. Really appreciate that. Looks like we already have our feedback link there in the chat, but if you have other questions, go ahead and type them in. We've got just a few questions for you. And I guess the first one has to do with specifically your area of responsibility there for the CWSU in Denver, and that is, is there anything that you need to take into account specifically with the smaller aircraft that fly to the ski resorts? I presume that one, with the mountain wave type turbulence, mountain driven turbulence there, and also some of the smaller jets, smaller aircraft, do they experience turbulence at a higher rate, and how do you communicate that?
Yeah, so certainly the smaller the aircraft, the worse the turbulence is going to feel for you. And even some of the more commercial airlines, actually, the way they are designed will feel turbulence more so than, say, other commercial airlines. And so in particular for the smaller aircrafts that are flying into We can issue a center weather advisory that discusses that particular thing in general, and we can specify that it's going to probably affect the smaller aircraft. And we can also say, you know, what heights. And typically, when you have lower turbulence in the atmosphere, say below 18,000 feet, that's typically going to be more towards the smaller aircraft, just because they're going to be able to feel that turbulence more so than a larger aircraft, say coming on approach into Denver. As for the ski country, the main concern with the ski country is snow, not so much in the way of mountains. There are mountains there, in a way, you know, surrounding obviously the ski country, but the main area that we see a lot of mountain wave activity is east of the Rockies. And that's usually determined when we have a really strong westerly jet that's moving perpendicular to those mountains. And in my experience, it seems like the more or the stronger the jet, the further east that will travel, the waves will travel and break to cause that turbulence. And then just a little bit back more about the ski country is with the snows, the problem is the orientation of the mountains and being able to get traffic in. Quite often, if we can't get traffic into those locations, they will be diverted to another location, which happens quite a lot during the winter, especially the ski months when people are headed out there during the Christmas time frame, basically from Christmas to New Year's is when is the busiest time for that part of the country. Matter of fact, Aspen can be so busy that it can be one of the busiest airports in the country, just due to that extra traffic coming in for the holidays.
Oh, that's really interesting. What were some of the tools that you used? I know turbulence has always been a challenge for forecasters. What were some of the tools you were using before you could resolve some of these more mesoscale features with GO16?
Yeah, that's a good question. So some of the things that we are using or had used in the past was we still had satellite. Granted, it didn't have the higher resolution, so we could see mountain wave activity if needed. And then we could go to the SQT, kind of like I did today, to show the levels where the turbulence was. But things that we were starting to receive over the last, I'd say, decade or so are higher resolution models. We did have the new NAM 32, and we also were getting in some of the newer, you know, RAP and things of that nature, which was really handy in terms of looking for some smaller features. We could actually put together, you know, I say a 4-panel of all the different models, the higher resolution models, and even the NAM 80, or sorry, yeah, NAM 90. So yeah, I would say certainly the model data was something that we would have to rely on. And now that we've got GO16, it's really good to be able to see, like in this case, you could see the turbulence dropping down based on that Meso-Scale vortex that was moving through the area. So I would consider that more of a short-term forecast feature versus something that a model would give us in the long term, because an AirMet is actually it's actually two parts. It's a forecast and an outlook over 12 hours. So in terms of longer term forecasting, the model data is what we could rely on.
Thanks. And related to the SQT, Mike Jamakowski just had a question about the SQT diagram you showed. And I guess he's looking at the wind direction change between 3 and 200 hectopascal. Is that something, that wind direction change there, something that you would normally recognize as a potential area for turbulence?
Yeah, I would, under normal circumstances in the winter, I would certainly look at that. That can certainly cause turbulence. When we look for turbulence in general, we both look for turbulence in the vertical and in the horizontal. And so in this case, yes, in the winter, no, not during the summer, just because 20 knot wind with a change in direction is not going to be something that's going to really affect the larger aircraft. You may feel it in a sense that it may be like a light turbulence, but overall it's not going to be something that you would feel that would cause, say, a SIGMET, which is a warning for turbulence.
Yeah, thanks. Yeah, certainly the speed is going to make quite a difference there. And I guess Walter Snell has a question here as well. He asks, is more turbulence felt when flying across the wave signature lines, along the wave signature lines, or across them?
Definitely across. Anytime that you're perpendicular to the wave, you're going to feel that. The main thing with the waves in general, and I like to kind of picture waves in a lake, and you can, for say you're sitting out on the lake and you are in a, like a air tube or something, then you're gonna feel those waves passing with you as you are on that lake. But as you get closer to the shore, and then when those waves are near where they're going to break, that's where you're going to find your turbulence. And so it's very much the same thing in the atmosphere as, say, for example, with mountain wave activity. You can actually follow that wave in an aircraft by going up and down with that wave. And then once you get to the location where that wave breaks is where you're going to get your turbulence. And so it's up to us to let the aircraft, or let the airlines, or anyone who's flying, really, commercial airlines down to general aviation, what is going on out there for them. And specifically for general aviation, they have to deal with the lower rotors that are coming off the mountains, that are basically in the lower in the atmosphere. Still wave activity, but just lower in the atmosphere. So good question.
Okay, thank you. We have a number of questions coming in here yet, but I'm going to wrap it up because I do know some people have to depart at the bottom of the hour here. Karen, I understand that you can stay with us a little longer to address those additional questions.
Yep,
And
sure
for
can.
everybody else that's able to stay on, please do so. We are going to continue the discussions. If you can't, though, I just want to remind you that next week, once again at 12 noon Eastern time, we will have a presentation from Sheldon Cusselson, a research associate at CIRA, and he's going to talk about the experimental advected layer precipitable water product. So watch for an email from the Tower S team on that. And again, just a reminder that please fill out our survey. Just like everybody else, we're asking for your feedback. We want to make this a worthwhile use of your time. So if you have to head off, I hope you're staying well, and I hope you'll join us next week. And for those of you that are able to join us, I'm going to go back and field some more of these questions. Okay. Next question here comes from Dan Lindsay. He says, for future geostationary satellite imagers, we're considering the addition of additional water vapor band, or of an additional water vapor band with a weighting function peaking even lower in the atmosphere. So we're looking at potentially seeing turbulence sub 500 millibars. Is that the kind of low-level turbulence information that would be helpful for the CWSU?
Yes, and actually that would be helpful for any aviation forecaster across the country, including the AWC. One of the things that is lacking in terms of forecasting for aviation is low-level turbulence. We just don't see a lot of model data for that, and I know that there are things that are in play right now that are working towards being able to do that, but really, realistically, there isn't much in the way of that below 10,000 feet, so below 700 millibars. So getting something that would be lower than that, or even below 18,000 feet or 500 millibars, would be very significant. So yes, I think that would be certainly be helpful.
Okay, great. Yeah, we're looking forward to GeoXO, which is the next generation program. And if you're interested in that, I believe we'll have another briefing on that program in mid-January. So a lot of exciting things happening there. Next question comes in from Tom George, who asks, are forecasters starting to use the new FAA weather cameras now available in Colorado to confirm forecasts? And I think there's also another link from Tom there in the chat to one of those cameras.
Yes, actually, in Colorado in particular, we rely heavily on that just because it's good to know where things are, what is happening, especially in waves of snow, because the radar in that area is actually obscured by some of the mountains. And so it's hard to know, depending on which way the snow is coming from, if it's actually going to start snowing. And we need to know that. We need to know when it's going to start snowing, because we need to let the FAA know, so they can, for a couple of reasons, if they need to divert aircraft to another location. Also, too, they need to know that there's going to be snow on the runway, so they can get rid of that snow so aircraft can come in and land. So yes, they are very, very helpful to know for the new cameras, especially, because that gives us a wide variety of different locations in terms of what we can see. So yeah, we really enjoy them. Great question.
All right. And see, I think Josajic here has a question. Would there be any value in calling for mesoscale sector imagery to track the wave features that you briefed on? So I think the underlying point of this question is, do they change substantially at 1 minute time scales to justify the use of a more routine, rapid scanning compared to the routine scanning from GOES-R?
That's a good question. One of the things that was brought up when we first started doing had GOES 16 was AWC actually does have the ability to request the smaller scales. And that was one of the things that we were wondering if we would be able, how would that help us in terms of forecasting? And realistically, I think it really wouldn't make much of a difference in a way that, we know that the waves are there, but we would have to look at some model data just to see what levels those were at, the waves were at, and also if they were breaking. Sometimes, depending on what the atmosphere is showing, and with the stability, the waves won't break. They will just continue on and dampen out. So I think it's certainly something to look into for the future as to whether or not it'll be work well with forecasting. But I think the just zooming in on a normal 5-minute loop would probably do well.
Sounds good. Another question here from Jammer. You didn't mention gravity waves from the dying thunderstorms over Oklahoma. Were they possible as a source of turbulence related to convection?
Yeah, so there was a lot of things going on there, more than just that MCV that was dropping out of western Kansas. You also had the dying MCS that was over eastern parts. Actually, can we bring up the satellite? Would that be something we could do? We can
Sure.
show that. And actually, if we could just bring up the 4 panel, because that's got the IR and the water vapor on it.
See if our technical team is able to work wonders here.
Yeah.
Sorry, caught you off guard there.
That's okay. Yep.
We can maybe take on
Yep,
this.
I'll try.
Go.
I'll try one more time here. Sorry.
If not, we can take another question while they try to pull that up. So while Lee's working on that, maybe I'll pose this other question you see from Scott Lindstrom in the chat, a little bit related, but the turbulence on that day was at about 30,000 feet, and you were using band 10 that has a peak in the water and the weighting function far lower than that. Of course, the satellite sees from the top down, so maybe you see all of the turbulence using band 10, but were there turbulence signatures in the 6.2 micron, which is the band 8, the more upper mid-level water vapor bands? Band 8 typically sees closer to the observed turbulence level for that day.
Yes, actually, I typically like the band 10, channel 10, just because I think it works well with mountain wave activity. But that day we actually did use all three. The higher turbulence, or sorry, the higher channel, there we go. We could actually see by adjusting the colors of the water vapor to see the waves in there. They weren't as distinct as they were in the lower band, but you could certainly see them.
Yeah, thanks. And I think that's a good point. As long as we have AWIPS up here, some of the field CWSU forecasters are with us, or field offices. One of the things we encourage in the training for looking at turbulence or identifying these waves is to sometimes alter the min and max range of the color table that are applied. And sometimes those subtle changes to that can really draw out features because there's really so much going on from very cold clouds to sometimes even land surfaces in the water vapor band. So the features that we have to draw out sometimes require a slight change to the min and max, and you see that being demonstrated there. But maybe, Karen, if you have anything to add to that, and also you can address this question about the gravity waves near the thunderstorms.
Right. Yeah. So just kind of go over what we were just talking about with that channel 10 is this upper right one, I believe. You can actually see there the wave that's not wave, it's kind of more a short wave, is moving through western Kansas down into parts of Oklahoma and Texas. And that's really what you could see with the way it was kind of starting to play out. And then when we went into the other channels is where you could actually see the waves themselves. But we did adjust, like I said, we did adjust the waves, or sorry, just the color in that channel, and that made those waves up in the channel 10 to actually stand out a little bit better. And then for the other question, if we could put a stop to the loop, that would be awesome. If you could stop it right. Yeah, this is perfect. So there's a lot going on here. You obviously have this feature that we discussed. It's moving out of western Kansas into Oklahoma and Texas, but you also have these thunderstorms that are dying out and actually through the afternoon will redevelop. And there's some discontinuity as well here that actually travels along, it's kind of along that front that they had drawn out that goes from just parts of northern Texas all the way through Louisiana and then all the way up into New England. And so that's, the discontinuity in the air mass is going to be a problem. And then, yes, this originally, when I was going through this case, I actually thought the waves were coming out of this MCS or dying MCS over eastern Oklahoma. But when I looked closer, I noticed that this dying MCS or MCV that was in the area was actually more of a kind of came in line with the time frame. So it's probably a combination of everything. The front that's in the area, the dropping MCV that's coming into the area, and the waves that are coming out of the dying MCS over Oklahoma.
Okay. And maybe just one last question here. One of the things I've always wondered about is, can you use data from satellite in particular to discern between areas of moderate or severe turbulence? So when it comes to issuing an AirMet versus SIGMET, are there any rules of thumb other than reports from aircraft that can help guide you in that decision?
It really just depends on the situation. As an example, there was a case back in, I think it was 2014, that there was an upper level low over New England that you could really see the shear on satellite, and knew that that was SIGMET worthy. And the reason I mean that is in terms of, like, if the water vapor was showing the really dark colors next to the, say, the whites and the grays, you could see that shear there. And we could, and so you can't really tell if it's turbulence or not, unless you start looking at, say, the model data that's pointing out the areas of shear. And of course, the time of year matters, because we just don't get a lot of turbulence in the summer and things like that. Turbulence in the summer is mainly caused by convection versus, say, dynamics in the atmosphere with, waves and things like that. So no, you can't really tell, but I will say that there for a while back in 2016, 17, I was using water vapor simulated water vapor model data to look for turbulence. And it was more so in as a yes or no. Is it going to be there or is it not? Not really on the heights. And again, that would only really work during the winter, not so much in the summer. So I hope that answered your question. That was a long-winded one.
Yeah, that was perfect. And this has really been a great presentation, really good engagement today. And I think at its peak, we had about 80 attendees from across the United States. So thank you for that presentation, Karen. And thanks for working those technical issues for us, Lee Byerly and Kashad Bowman. That's been great today. Really appreciate it. So with that, we'll give it the final wrap up here, and I'll just point out once again that we do have a GOES-R guide for accessing data. If you're looking to play with the data from GOES-R series a little more, and of course the feedback link is also in the chat. So with that, hope everybody has a happy holidays, and you'll be joining us again next week for our presentation on precipitable water. Take care. Until then, bye now.